Welcome, everybody. My name is Marc Richards, and I'm going to kick off all of the sessions by actually talking about testing software architecture. However, before I start, I did want to give a shout out to all of the sponsors to actually help make this wonderful conference happen. So thank you, sponsors. I think they're all in there, but anyways, if any of them are here, thank you. Most of you probably were at home for the past 2.5 or 3 years, as was I, and tried to make use of the pandemic. And as a matter of fact, my friend Neil Ford and I ended up publishing 2 books during the pandemic. In 2020, The Fundamentals of Software Architecture, and then in late November 2021, The Architecture of the Hard Parts. Now, in truth, the Fundamentals of Software Architecture actually took us about 7 years to write. It just ended up getting published during the pandemic. But the Hard Parts, of course, was just 2 years. So some of the material that I'm going to be showing you does come from these books. So what does it mean to test software architecture? Why is testing software architecture so important? This is why. So what you see in this picture is a bridge over some sort of river, and that bridge represents that structure, just like our architectures, and there's the cars going through it. The structural integrity of this bridge is fine for that amount of traffic, but what happens as time goes on? Systems start to grow, and like this town, this same bridge starts incurring a lot more traffic, a lot more requests, a lot more users. And if we don't pay attention to the structural integrity of our architectures, our structures, this will unfortunately happen. This is why testing software architecture is so important and so critical. Okay, so let me start this talk by actually showing you an example. Let's suppose we have a system that is for students to take standardized testing all across your country. And students go to their classroom, they sign in, and they're presented with questions and take a test. Okay, so that's the system that we have, the application. And the flow of that system looks like this. We have students. Now, we could have anywhere from 20 to 120,000 students all signed in taking these standardized tests in your country at the same time. So students sign in. Once the test starts, they get presented a question. They look at the question, they answer it. Once they answer it, the next question is then presented to them. Now, asynchronously, what's happening is that that question that they answered, their answer gets graded and then stored in a database. Okay, that's pretty simple. And as a matter of fact, most of us are familiar with what to do with this kind of system. We write code, and then we write unit test cases. This is second nature to every single one of you. As a matter of fact, this particular test case just tests a user sign-in. So we write unit tests for all the functionality. We go and execute that test. As a matter of fact, let's execute this, and looks like it passed. Fantastic. This is the architecture for that student assessment testing application. Notice we've got on the left-hand side, I think it's left-hand side for all of you, yes, sort of the admin portion. On the right-hand side, the actual test taking. Question. What does it actually mean to test an architecture? We all know what it means to test the functionality, the system. We do that every day. At least, I hope you're doing that every day. Okay, yes, of course. My good friend, Venkat Subramanian, many years ago had a great quote about testing. He said, testing is like exercise. We all know we should do it, and we know it's good for you, but none of us like doing it. I like that equation of testing and exercise. But what does it mean to test in architecture? When we test architecture, as opposed to the functionality, essentially what we are looking for are elements of structural decay. Walk around the city or your country and take a look at these big pylons holding up the highway bridges. Take a close look at them, or any kind of building, and you'll see some cracks. That's elements of structural decay. Now, all pylons have some cracks, but what we're really looking for, and essentially what we're doing when we test software architecture, is looking for those cracks. Too many cracks, well, and you can guess what's going to happen. That bridge will collapse, or that highway bridge will fall down. So there's two things that we can actually do when we're testing software architecture. Two types of ways of testing architecture. The first are operational characteristics. Those things like scalability and performance and all that. We can test those things. But we can also test the structural integrity of that architecture. That foundational aspect, like that bridge, that's holding up our systems. Now, when we look at either of these kind of tests, which we'll look at right in this session here, we're really asking three main questions. First, are changes that we're making to the functionality impacting the integrity of that architecture? Number two, are changes to our environment, whether it be technical or social, impacting the integrity of that architecture? And finally, a third thing, and that is, can we actually verify and demonstrate the integrity of that architecture? We all write unit test cases, scenario test cases. We execute those. We get results back like we did on that screen when I ran that Python unit test. That's a demonstration that our source code works. But what about the architecture? Does it scale? Is it structurally sound? Is it close to imploding? Actually, imploding would be this way, wouldn't it? Exploding, or usually applications simply implode. Well, let's take a look at each of these types of ways of testing software architecture, independent of the functionality. And let's start by taking a look at those operational characteristics. Operational characteristics, what I usually call architecture characteristics, are things that some people call non-functional quality attributes, system quality attributes, the ilities. I don't like non-functional requirements or non-functional system attributes. The reason is, if you're having a conversation with somebody, especially a business stakeholder, and you say, excuse me, I'd like to talk about the non-functional, it doesn't matter what you say after that. No one's going to listen. System quality attributes I'm not fond of either, because it has this implication of this final kind of last polish on the application before you set it out to production or release. And it's not. It forms the beginning of these. However, these are things we can actually measure, generate metrics from. But there's a problem, everyone. These are largely poorly defined. Now, most of us know what scalability is or availability, but let me ask you a question. What's reliability? How do you define reliability? We are charged with making sure that our systems are highly reliable. Yeah, okay, I can do that. We all know what it is. But how do you define it? You'll have to speak really loudly at the top of your lungs. But how would some of you define reliability? It's kind of hard to define, isn't it? It's like I know what it is. Like my car is reliable. Why? Because I go to my car to go to work or go to the pub. Well, I wouldn't take it to the pub. But it starts up. I don't have problems with it. Here's a little trick, everybody, that you can use to define every single one of these characteristics up here. And you ready? Here's the tip. If you can measure it, then you can define it. So let's turn the equation around. Reliability. What would you measure to determine if the system is reliable? Think about that. What would you actually measure? How about availability? Is the system up when I need it? I can measure availability. How about when errors occur? Error rates. I can measure that too. How about when an error occurs? Did the system crash or did it recover quickly? That's fault tolerance. I can measure that. When I go to place an order and I get an order ID back and I go to query that order, is it what I ordered? That's all about data integrity. Something else I can measure. So do you see, we can start to now define for your particular scenario what reliability means. Availability, fault tolerance, error rates, data integrity, all of those pieces. Okay. So one way to actually then measure these operational characteristics is something that I'm sure all of you are going to hear so much about in these next 2 days in a lot of talks. And those are things called architectural fitness functions. Now, this was first coined in the book Building Evolutionary Architecture by my friend Neil Ford and then Rebecca Parsons and Patrick Kwa. And an architectural fitness function provides some sort of objective integrity assessment of some sort of architecture characteristic. And when I say objective, I mean an actual numerical number that I can demonstrate and prove. Now, there's a lot of tools, some of them that you will be seeing today and also tomorrow, that can be used to actually measure the metrics of these operational characteristics. But I'm not going to go into those tools because a lot of other people are in these next 2 days. However, let me describe how an architectural fitness function works. So we have our system, our website, our application. And through observability, we stream whatever metrics are interested to us. We can stream that through something like Kafka. We can use message queues. But the point is we get that information asynchronously out to someplace as fast as possible. Then we write a capture service to be able to read those topics and then store all that raw data. Now the fun part comes. Now we get to write analytics services that actually take that raw data and start measuring that data, tracking that data over time. And that tracks until we reach a trend or a threshold to alert me. And that's how a fitness function works. Okay. So, we can do 2 types of fitness functions. Those that are trend-based measurements. These tend to be most of my favorite ones, where we're kind of looking over time to see if things are getting worse or getting better over time. And then it notifies me if that analytics service that I wrote through simple machine learning or just basic trend analysis starts to notice something's off. But there's other fitness functions you can write that are threshold-based. In other words, notify me if all of a sudden I reach a certain threshold. Let's say that we have a service level agreement or a service level objective that says we never can exceed 2,000 milliseconds response time. So notify me if that occurs. And that would be a good example of a threshold-based. So before I show you some of these based on our standardized testing application that we're going to look at, and actually look at how to write some of these fitness functions, and actually test our assessment testing application, there's another question I want to ask first. When should we test software architecture? Well, of course, the answer is always. But what I mean by when is, where do I place these tests? Because I really do have two options. When I test software architecture, I can do what's called triggered fitness functions. Triggered fitness functions are a hook inside our CI/CD pipeline, where as I'm doing a release or a build, I can actually execute these fitness functions against the architecture. The other are continuous, that basically run in production. All right, let's take a look at each of these, because this is a question we will have to answer. Where should or when should I run these tests that we're going to be building right in a little bit? Triggered fitness functions have a great advantage, everybody. And the key advantage of that is that we get notified that we broke something in the architecture early on, before the production release. And obviously, that's what we want to do. Or is it? Because when we have a triggered fitness function, we have three problems that could occur. Do occur. The first, we have to maintain those tests. And that's not only expensive, but it's probably the most horrible job you could have. No one wants to do this. No one wants to pay for these tests. But even worse, we have to maintain corresponding test data and the volumes of that data. But it gets even worse than that. My negative experiences with triggered fitness functions are really trying to model user behavior. Getting the appropriate level of volumes of data, the types of actions a user would take, is actually really hard. And what happens is sometimes when we're doing load testing for scalability or elasticity, we'll start to hit a particular area in the database that might not actually represent the true data distribution. And all of a sudden, we go from row level to page level to table level locks, and boom, all of a sudden we can't scale. But that's not accurate in our production environment, because we're trying to simulate that user behavior. So we can see that there's trade-offs involved with this. The first being early detection, but all of this stuff. Let's take a look at continuous fitness functions, though. With continuous fitness functions, the great advantage is that there's no load tests or test data to maintain. There's no modeling of user behavior in user requests, because these are running continuously in a production environment with real user scenarios, real data volumes. So there's no tests or test data I have to maintain. You know, the other thing is we do measure actual volumes and that distribution of user behavior. Third, this allows us to, a little more easier, actually a lot more easier, to basically model trends over time. You know, if I'm running a load test or to measure scalability or elasticity or availability, and I'm doing that as a triggered fitness function, sure, I can kind of record that information and then replay it back and build it every time I test, but that's rather difficult. Here, I'm just getting a stream of data coming in, and I can kind of look at the trends over time based on some sort of context. However, oops, I thought we were there, but we're not, because now I find out problems after we release into production. So we can kind of see there's some interesting trade-offs between when to use these fitness functions. Triggered, which is great because I get early detection, but they're much more expensive, much more effort, and a lot less accurate. Versus continuous fitness functions, running in production. We don't even know they're running. Just alert me when you see a problem. Otherwise, leave me alone. But we have later detection, but it's a lot less effort, a lot less cost, and much better accuracy. So which is more important? If you absolutely cannot afford for that bridge to crack or fall down, then we have to do triggered. If you can, it's a lot more effective and less effort to do continuous. All right, let's go back to our student assessment testing system. Now, there's two most important things that the education department told us about this system. The first, it is absolutely imperative that we don't lose any student answers in case of some sort of system failure anywhere in the architecture. We can never lose a student answer. Number two, during the day, during a testing session, we could have anywhere from 20 students to 120,000 students all taking the test at the same time. And what that means is we could possibly have 120,000 students all at the same time answering a question and getting the next one and saying, don't know, next, don't know, next. It's 120,000 requests a second. That's pretty high levels of elasticity. Well, we built the system, and I have the architecture here, and here's how it works. So, what I have here, first of all, is the test taker, this middle service right here, receives the student answer. It submits it to a queue. Once I get verification it's in the queue, I then deliver the next question to the student. The auto grader, meanwhile, dequeues that student answer and then compares it against the answer key to see if it's correct or not. And then number three, the auto grader inserts it into the student answer database. Is there any data loss problem here? Will this scale to 120,000 users potentially? That's what testing architecture actually means. Irrespective of the functionality, we're testing the operational characteristics of the system. Let's start with the data loss. Let's write some fitness functions to see what it would look like to actually test an architecture. So starting with no data loss, what could I do? Here's an example of a pretty simple fitness function. First of all, I can do a student answer checksum. So this is actually fairly straightforward. Now notice, as I'm thinking about and writing these fitness functions, that's going to require a certain level of observability in my services. How does a developer know what observability to write into my services? From me, the architect who's responsible for these particular architecture characteristics. That's where the collaboration is required. Where if I want to run a test, I need you, the developers, to be able to produce those metrics. So, I could record the number of test answers submitted from students. Test taker knows that. I can actually record the number of answers the autograder dequeues. I can stream that out. I can also do a query into the database to find out for that testing session how many answers were recorded. Now, all of these should equal each other, but we have a little bit of a problem because I was not quite accurate when I said this is a fairly straightforward and simple fitness function. Why? Here's why. Those three numbers will never be equal during testing. Oh, right, because this is all asynchronous. So, I need two more pieces of observability. You know, isn't it interesting? Most of the time when we say observability, we're talking about a particular service sending out some information, streaming it or sending it to some sort of message queue asynchronously. Well, what I would have to do is write a fitness function to track all three of these, but not compare them until two events happen. The first event, all the students have signed off for the day. That's event number one. Event number two is that the autograder is now idle. I've dekeyed everything, I've answered all the grades, I've graded them, and I've stored everything in the database. Both those services know when that happens. And so thinking about these fitness functions early on, these will be user stories. Okay, so now I compare these, and this is what it looks like behind the scenes, because this is just continuous, running in production. And notice for each testing session where students sign in, take a test, and stop, everything is not fine. This is the reason we test architecture. Because notice, we submitted more than we graded and put in the database. Knowing that the retrieval of that message from the queue and the database are the same, that means somewhere between the test taker going to the queue and reading it, we lost data. Now, that's bad news, but now that's a placeholder to investigate, research, and plug that hole. Okay. Let's look at a little more interesting aspect, and that's elasticity. Elasticity, unlike scalability, is really those unexpected or expected peaks of user load instantaneously. We go from 20 users to 120,000 within a couple of seconds. That's an elastic system. Then it goes down to maybe 50,000, and then it goes up to 70, down to 40, back up to 120,000. This is just described an elastic system. Is this up here elastic? Will this maintain 120,000 users? It looks like it will. I mean, I've been an architect for 27 years. I'd hope at this point I know what I'm doing. I don't know. The builders of that bridge that we saw collapse knew what they were doing, and the bridge collapsed. Let's test it. So one of the first things we can do, which is the most obvious definition of elasticity, is regardless of how many users I have concurrent in the system, my response time remains consistent. I can measure that. So on sign in, I basically gather all of the response times and the corresponding timestamps and student IDs. And I do the same thing for test taker. These are metrics I can stream out from each service. And now I write a fitness function to track those response times based on user load. And this is what that analytics service that's now reading that raw data from that fitness function looks like. As we start going through testing, notice we have peaks and valleys, which is why I like trend, by the way, over threshold, because sometimes it goes a little high, but then it calms down. And as a matter of fact, case in point, notice if I were to draw kind of an average mean across these, regardless of the number of students I had, everything's within about a 1 standard deviation. This is something else I can bake in or write into that analytics service. It's basically, if it stays within 1 to 2 standard deviations from the mean, then we're good. Oh. But notice we had a little bit of a problem here. The response time started to go up. However, if I were to generate this kind of graph, because this is all just running behind the scenes, I realize that was an immediate increase in user load. And it can be explained because I was probably starting up additional instances of my test taker service to respond to that increased load. In which case, notice then it starts to go down right away. That's why trends are so important to measure as opposed to the exact values. This system works fine from a responsiveness standpoint. Remember that question number 3? Can I verify and demonstrate that this architecture is structurally sound? Yes, I can. There's the demonstration right there. We don't need to talk any further. As a matter of fact, there's a couple of other things I can actually test as well. I could test the autograder throughput. You see, what we've been looking at so far is from the student's perspective. Now, that's an important measurement. It's an important metric. It's an important test. But if the rest of the system can't respond to 120,000 students, those queues are going to fill up and everything's going to fall over. So what's the throughput of our autograder gathering these questions? Because it's writing to the database, it will be slower than the number of questions put in. Well, one of the things I can measure is the queue depth of every one of those queues. So every minute or so, I just simply query the queue depth. How many pending student answers are in those queues waiting? It's a great way to measure the throughput of our autograder, because as we make changes to the grading portion, am I impacting that throughput? That's an important thing to know outside of the functional tests. So let's write that fitness function. And as a matter of fact, I look at the queue depth over time. Testing starts, and notice the queue's kind of up and down, up and down. But overall, this is another good demonstration about the fact that regardless of the number of students, 20 to 120,000, that autograder kept up. But keep in mind, this is not a snapshot. Actually, it is, a snapshot. But it's not meant to be a snapshot. This keeps running to always compare. Did changes to our code impact this? Did changes to our environment impact this? It's the importance of continuous fitness functions running continuously in the background. One last thing we can test with elasticity, which is kind of interesting, is another one of the definitions of elasticity. When we talk about scalability versus elasticity, scalability is about sustained growth in our systems. We get more users, we add more functionality, users start using the system more, there's more requests made in the system. Maybe we are involved in acquisitions of other companies, so we're getting new books of business along with those customers. Do we have enough capacity in our database? Enough capacity in our servers, our virtual machines? Is response time impacted? That's a good definition of scalability. Elasticity, though, means right now I just got another 120,000 users. Concert ticketing systems are a great example of elastic systems. Oh, there's a few users hopping around in the system, but when a major rock concert gets announced, one of our favorite concerts, what happens? The millisecond those seats go on sale, we've got tens of thousands of users all vying for those front row seats. Do you know what structurally, architecturally, the core difference is between those two scenarios? How fast can I respond to that immediate increase in user load? And that's a function of something called mean time to start, MTTS. The slower it takes a service to start up, the less responsive that system will be. If I have 200 classrooms that unfortunately all start the test at the same time, oops, I could not have predicted that. I need to respond immediately. How fast can that test taker start up? That's another test, because this is another metric I can actually observe from that test taker. So I measure the startup time, and I write a fitness function to track that. either triggered or continuous. And this, folks, is what that looks like. Things are pretty good. All of a sudden, uh-oh, did you notice what happened? It almost doubled. Do you know why? Because that was a new release of our software. Functionally, all tests passed. Structurally, they didn't. And as a matter of fact, this is the point where we found out about that problem and then the next iteration fixed it. These are all the kind of examples of metrics that we can stream from an observability standpoint from our services to be able to test the operational characteristics. But let's end this session by talking about another kind of testing, and that's the structural integrity of the system. So ignore all those operational things. What about the overall structure? Is the internal structure of our system sound? Let's take a look at a different example. A typical e-commerce site. Well, we've got order placement to place an order, inventory management to manage inventory, stock ordering to replenish the stock, item pricing to raise the price up and down, and finally notification. Well, when I go to place an order, what happens? And by the way, these are all architectural components. When I start talking about the structure of our system, the architecture, what I'm talking about are those architectural components. All of these may be components manifested through a namespace, maybe a package structure in Java, a directory structure. That's what manifests an architecture component. All that code grouped together that does one thing. These could be separate services. These can all be in one large service. But these are just components. So I place an order. Is it my responsibility to decrement the inventory? No. I have to tell inventory management component to do that. Now, if these are bound components, I would make a method call in a different namespace or package structure. Is it my responsibility to notify through email? Nope. That's email notification. If it's a service, I send a RESTful call. Maybe I invoke a method. But there's a couple of other things that happen, because if our inventory goes too low, I have to order more supplies. Not my responsibility. That's the responsibility of order supply. And finally, the lower the inventory goes, the higher the price goes. So now I have to increase the price if the stock goes too low. Not my responsibility, but I have to tell somebody to do it. Do you notice a problem with the structure of this system? I sure do. It's right here. That order placement is highly coupled to the entire system. Changes to that, even if it was a service, are really going to impact everything. I want a looser coupled system. So creating loosely coupled systems is applying something called the law of Demeter. The law of Demeter, otherwise known as the principle of least knowledge, comes from the name from the goddess of Demeter in Greek mythology. She produced all the grains in the world. That was her responsibility. She did not know what you did with them, and that's where it gets its name from. The less you know about the system, the more decoupled you are. Hence, should order placement even know that we have to order more or change the item price? No. Less knowledge, less coupling. So, we don't want these two coupling points, but rather we move them to inventory management. Now, order placement is less coupled in the system. That's what the law of Demeter is. Okay, little piece of trivia there, but that's our architecture now. How do I maintain that structural integrity? How do I ensure that that order placement's not going to talk to anybody else? Fitness functions. These are different kinds of tests. Some of the tools you can use, for example, in Java, is ArcUnit. In the .NET environment, ArcUnit Net, NetArc Test. As a matter of fact, even one of the sponsors, Hello Tomorrow, SonarGraph. All of these tools allow us to codify, meaning write programmatic code for our constraints, our structural integrity in the system. So let's take a look and come back to this and say, well, how do I ensure that this remains as is and that developers don't choose to maybe call something else from order placement? Fitness functions. For example, with ArcUnit, which I'll just use as an example, notice the name of this method. Placement can only access notification and inventory. This is a test, folks. This has nothing to do with functionality. It has to do with structure. Classes that reside in a package app.placement should only access classes that reside in a package notification and inventory.check. There's a test I can place into a hook within an IDE, my CI/CD pipeline. Hopefully not a commit, please don't. But this is a triggered fitness function, which I can place anywhere in the development process. As a matter of fact, here's another interesting one. Let's say that we have a traditional layered architecture, n-tiered architecture. But I don't want the presentation layer talking directly to the database because we expect a lot of change in that database and correspondingly in the persistence layer, and I want to isolate that change just to the business layer. I don't want my presentation layer having to change as well. Okay, that's a good reason, justification, but how do I maintain that structural integrity? This is how. Presentation layer cannot access persistence layer. Don't do it. Yeah, whatever. But it's faster, so I'm going to do it. No, you're not, because I have this structural integrity test in our system. No classes that reside in presentation should access classes that reside in a package persistence. Now, notice what these tools have. This clause right here, which is so important to use, because in my experience, I can almost guarantee you any decision involving the structural integrity of our architectures and our systems will be violated. But sometimes the developer doesn't know why this test is failing. This tells that developer why it's failing. Okay, but let's do a harder one. Let's do something a little more difficult. Let's say that, let me go backwards one here. I've got another layered architecture, but we're going crazy with shared objects everywhere. I want to try to kind of maintain the control and keep all those shared objects in the same place. So we're going to create a shared services layer. All shared objects used by the business objects in the business layer have to reside in the shared services. Don't put them anywhere else in the system. Really? I show this one because, like the operational characteristics, sometimes when we devise these tests, there's additional work for the development team. And here it is. For example, in something like ArcUnit, it would look like this. Classes that are annotated with shared service.class, therefore there's a custom attribute or custom annotation, should reside in a package services. That defines that layer. So in this case, we have an additional annotation I now need to apply to all my shared service classes. Well, let me finish up with this one because this one I'm really fond of. When I do monolithic single deployment applications, whether it be the layered architecture, modular monolith, or even the microkernel plugin architecture, this is a great test. So, for example, in ArcUnit, ArcUnit.net, they supply something, whoops, I went the wrong way. They supply something called layered architecture. Now, what this test is doing, and this is amazing, folks, this test is describing the structure of my system. Now, I use this for domains, I use it for components, I use it for plugins, all that kind of stuff, all three of those kind of architecture styles. But here, .layer could see .domain, but I use .layer and define it as one of my domains in the architecture, defines all of my various layers. This section defines all the constraints of who can talk to who. And if there's any class in one of those packages or namespaces that tries to talk to something else, fail. These are great tests. So what we've seen in this little journey are a couple of things. First of all, testing the architecture is as important as testing the functionality. Number two, we can kind of test through operational characteristics. And we can also do entirely different tests based on the structural integrity of our systems. So please, please, use this knowledge. Add testing software architecture to your regular daily life as you're testing functionality. You don't have to be an architect to test architecture. These tests are software. We can write them. Without it, without doing this, the bridge will fall. Wonderful. Thank you all so much.
Hello. Hi. If you have any questions, just raise your hand, or you can also use a mobile app. There is a Q&A section in Marc's talk. So yeah, you can use these two channels.
Great.
Any questions?
Yes.
Thanks. You said that in triggered fitness functions, you prefer the continuous one and operational aspects. And I was thinking about the trade-off you showed. Mm-hmm. And one of the positive points of having a triggered fitness function about operational aspects, I think, is also to be able to simulate future loads with respect to the actual load in production. Mm-hmm. If you just use continuous fitness function, you can't simulate what may be in the future. So, for example, you measure what's going on in production, you get some throughput information, and then you multiply by 3 and test your system before you are going into production. Okay, that's just maybe a comment, but I would like to...
and it's actually an extremely good comment, because I do have a response to that. And you are absolutely right. Fitness functions, continuous fitness functions, don't predict expected future load. We're about to do an acquisition. Is a great example. Will our systems be able to handle that? Well, I want to find out now, not in the future. This is a perfect example of where I might use both. So just the normal everyday running, I would have continuous fitness functions running in production. But for these kind of cases, these are great examples of writing triggered fitness functions to make sure that our systems will be ready to go during that acquisition. And so this is a perfect use case for saying, well, why don't we use both? Sure. I wouldn't always use the triggered, but in these kind of cases, that would be a great example. So yes, really good point about the future load or expected load. Yeah.
Okay.
Oh, do we have time or?
Yeah, just several questions more.
Hey.
Just a second.
Hello.
Okay, so we have one online question. Is Arc unit only usable for monolithic systems, or at least within monorepo?
So if I understand the question is, Arc unit and all these only available or only useful for monolithic applications? Mostly the answer would be yes, although I can still use those within any given service. Many times within distributed architectures, especially when we're using multiple repositories, is I will create a virtual repository from all those separate repositories and then run some of these tests through there. Now, that said, there are some things and some constraints that extend beyond what these tools can do in distributed architectures. But for any given domain service, I can certainly run these tests, but they do become more difficult, or in some cases not usable, between multiple services, or especially in microservices.
All right, thank you.
All right.
Actually, we have a lot of questions, but unfortunately, we don't have enough time for them. We will have coffee break. Marc, you will be there as well, right?
Absolutely.
So what we encourage is just to continue questions and answers there.
Yeah,
and you can ask
hunt me
all the
down.
questions.
Exactly, Ekaterina. You could find me in the other room over there. Just approach me and we can talk about your questions. So awesome, thank you.